Right. This is a talk I gave at the MIT and Harvard a couple of days ago on large-scale hydrodynamic instabilities in protoplanetary disks. I think it's a good time to be interested in large-scale structures in protoplanetary disks because we can now observationally actually see these structures. These are observed images of transition disks, and these are disks with apparently holes, inner holes in their dust. And the point I want to make with these plots is that these transition disks do not appear axisymmetric. There is clearly some sort of non-axisymmetric structure around the hole. For example, this plot here, there are two distinct blobs, and here there is a dip uh, next to the hole. So understanding where these structures come from will give us a good understanding of the underlying disk structure. Now, what I'm going to talk about in this video is the possibility that perhaps these large-scale structures come from some kind of dynamical instabilities that's associated with the fact that you have a hole in the system. Okay, so large-scale structures in protoplanetary disks are there are a couple of applications for these. For example, angular momentum transport. Also, one structure I'm going to talk about is vortices, and vortices are known to be able to attract dust particles, and perhaps that would lead to, or at least help, planetesimal formation. Having these large-scale structures in the disk will certainly affect how solids move in the disk, including how planets move. And the instability, which I will discuss, may be naturally associated with the disk structure itself. I mean, protoplanetary disks may have complicated structure. They may not be nice power law functions of radius. So this is a schematic cartoon of a protoplanetary disk. Now, this is one of the conventional models of a protoplanetary disk. Everywhere in the disk, the angular momentum transport is through the magnetorotational instability, except a region called the dead zone. Now, in this so-called dead zone, the turbulent viscosity due to MRI is believed to be low because the magnetic field is not well coupled to the gas. So the point here is there may be a transition in the disk properties. For example, in going from the active outer regions to an inner dead zone, or from a dead zone to an inner active region. And at these radial boundaries, because the disk properties change, we might expect things like the density to go through a large change as well. For example, there may be some sort of density bump in the system. So it's then reasonable to ask what is the stability properties of localized structures in protoplanetary disks, and if they are unstable, what are the possible consequences on or implications on planet formation and the disk evolution. So I want to start this talk with a couple of examples from computer simulations. So in order to model that localized transition region, which could be due to this active dead zone boundary, a simple thing to do is take a disk. So here I've got a disk, and it's a smooth disk, except I've put in it a density bump. So here's the density ring here. And it's well known that a localized ring like this is unstable to what's now called the Rossby wave instability. It is really a Kelvin-Helmholtz instability, except in a differentially rotating disk. And there's an instability which comes about for the following reason. Imagine this solid line represents that bump, that localized bump in the previous slide. Now, it turns out that at the bump edges, for example, in the inner edge and outer edge, there's a disturbance that can be supported called Rossby waves. And the waves are such that it has a negative angular momentum inside the bump radius and a positive angular momentum outside the bump radius. This comes about from the fact that the wave has a frequency which is smaller than the rotation frequency if you're inside the bump. And if you're outside the bump radius, the wave frequency is faster than the background rotation frequency. So we have a pair of oppositely signed disturbances on either side of the bump. So, and there's an instability which comes about because angular momentum is generally transported outward. So the angular momentum would be transported from this wave to this outer wave. So the inner wave will become more negative in angular momentum, and the outer wave becomes more positive with angular momentum. And that is a feedback loop. So in practice, in the nonlinear regime, if you simulate this for a couple of tens of orbits, then you will find vortex formation. So this is a simulation I did with the Athena code. It's a three-dimensional disk, but in a box geometry. Now what I've plotted here is the density perturbation. So I've subtracted off the background bump. What you see here is the pairs of disturbances on either side of the bump radius. So that represents two waves on either side of the bump radius interacting with one another. So the original axisymmetric ring is now broken up into four distinct blobs, and we'll call these blobs vortices. Now there are four blobs here, but it's not actually due to the square geometry of the computational box. M equals 4 is actually the most unstable mode for the system. Here's another example. Again, this is a three-dimensional disk, but in spherical geometry. And this is done with the Zeus code. So again, I've put initially an axisymmetric bump and just let it go. And this particular simulation includes self-gravity and an energy equation, but qualitatively very similar result to the previous plot, which is the fact that the original ring breaks up into non-axisymmetric vortices. Now you can also put in some kind of a mechanism to form these localized structures in the first place. For example, here, these are two simulations done with the Pluto code. On the left here, I've imposed, so both of these are three-dimensional disks. On the left pair of plots here, I've chosen a viscosity profile such that the inner disk has high viscosity, while the outer disk has low viscosity. Now, because there's a viscosity difference across this boundary, there will be mass buildup around that boundary. And this boundary region becomes Rossby unstable to vortex formation. And on the right here, these are, this is again a three-dimensional simulation with self-gravity, but now I've put in a giant planet in a disk. So this is a 1 Jupiter mass planet in a disk, and the disk has very low viscosity, and it's known that in that situation, the gap edges become unstable. So the giant planets generally open gaps in disks, and if this viscosity is low enough, then the gap edges are unstable to this Rossby wave instability. Now, as I said, there are two main applications for this vortex instability. The first one is angular momentum transport. So these are simulations done by Vladimir Lira. And so he did a non-ideal MHD simulation where he's imposed a jump in the resistivity profile. So in the inner disk, it's MRI active, and in the outer disk is MRI inactive. So the outer region is meant to represent the dead zone. So what he found was in the dead side of this transition region, he finds vortex formation. And when he measured the accretion rate in terms of this non-dimensional alpha parameter, he finds an alpha parameter of about 0.01 in the dead zone, and it's actually about the same value in the active zone as well. So this vortex instability can provide angular momentum transport to such that you can have accretion across this apparently dead zone boundary. Now the second application, and maybe this is the more application which is attracting more attention, is planetesimal formation. So these are, again, simulations done by Heloise Mayhew, and what she did was she took an RWI unstable disk, so the disk becomes Rossby unstable, you form vortices, and then she's added dust to the system. Just see what happens. We'll just look at the leftmost plots here. Where my mouse is, this is a plot of the density field, and where there is high density, that's where this vortex formation has taken place. On the right here is the dust density, and you can see a good correlation between where the high gas density is and where the high dust density is. That is to say, this vortex is concentrating dust into its center, and that clearly may help planetesimal formation. So these vortices may act as particle traps. Now, these are nonlinear simulations. But this instability is a linear instability. That means the starting point of all of this is an understanding of the linear stability of radially structured disks. So the Rossby wave instability the name was coined by Richard Lovelace in 1999, where he looked at a two-dimensional disk, non-self-gravitating, but including an energy equation. And the disk also has some kind of radial structure. Now this sort of standard configuration has been generalized, but only recently. For example, some people have included self-gravity or magnetic fields and three-dimensionality. So what I want to do in the first part of this video is to try and generalize those 3D results to polytropic disks and adiabatic three-dimensional disks. Now the adiabatic 3D will be a more direct extension of the original 2D calculations to 3 dimensions. So the linear stability problem in 3 dimensions is very complicated. So this is one of the more general partial differential equations you can write down for this kind of problem. And it's complicated because this is a two-dimensional complex equation, and there are potential singularities as well. But it is important to do this kind of calculations because for me, the main application would be, this is a linear calculation which I can then use to check my hydrodynamic simulations, which is really the basis of all my work. It's hydro simulations. But without a calculation like this, there's no way of telling whether my hydro code is doing the correct thing. So anyway, that's a bit of motivation. So I want to start with the linear problem for 3-dimensional polytropic disks. So what I mean is the pressure will be related to the density field through a simple power law, with power law index n being the polytropic index. And this relation is going to hold at all times, both in the equilibrium state and in the perturbed state. So we set up a axisymmetric disk, vertically hydrostatic. It's a smooth disk, except you put in a density bump at unit radius. So we linearize the fluid equations, go through the standard procedure in obtaining a single partial differential equation, operator L acting on the perturbation variable W, which is the enthalpy perturbation for this problem. So L acting on W is 0, and we want to solve for W, which is our eigenfunction. The operator L depends on both the cylindrical radius and the vertical height. It also depends on sigma, this eigenvalue of the problem, which determines the time evolution of the perturbation. Now, in the linear operator, sigma only appears through this quantity sigma bar, which we will call the intrinsic frequency of the mode. So the Rossby wave instability is a special solution to this problem where the real part of this intrinsic frequency is 0 at the bump radius. But strictly speaking, what I mean is the real part of the frequency is 0 at the location where the potential vorticity reaches an extremum. So we're going to look for solutions of this type. Now, the operator L is very complicated, even for numerical work. But there's a very special property for polytropic disks, and it's the fact that the polytropic density field looks like this. It is the midplane density multiplied by a vertical stratification function. The vertical stratification function is 1 minus the height divided by the disk thickness, all squared to some power. And it turns out that for this particular functional form, you can look for solutions in terms of these Eigenbauer polynomials. So the enthalpy perturbation, that's our key variable, is going to be written as a series of radial eigenfunctions, WL, multiplied by one of these orthogonal polynomials, which takes care of the vertical dependence. And it turns out that if you insert this expression into the original partial differential equation, you can convert the original PDE to a set of ordinary differential equations. Now these operators L, AL, BL, and CL, they all depend on the cylindrical radius and the sigma. only. So in summary, if you assume this form of solution, then you can remove the vertical dependence in the linear problem, although it does involve a fair amount of work. But this conversion from PDE to ODE is exact, and so is exact without approximation, and you can do it by hand, but you do need to assume certain vertical boundary conditions. So anyway, let's look at some solutions to this linear problem. I want to start with this problem, which is this is a smooth disk with a density bump. What I've plotted here is the potential vorticity. So the potential vorticity is inversely proportional to the surface density. So if I have a surface density bump, that means I have a potential vorticity minimum. And I'm going to look for solutions where the disturbance is mostly associated with this minima here. So that is to say, the boundary conditions imposed at 0.4, 1.6 won't be a crucial factor, won't affect the solution too much. And it's also important to note that in the non-magnetized, non-self-gravitating case, the Rossby wave instability is associated with potential vorticity minima only. So here's the solution to the linear eigenvalue problem. Remember, the original perturbation variable W is being written as a series of radial eigenfunctions multiplied by one of these orthogonal polynomials. But in the plot here, I'm just plotting the radial eigenfunctions part. And we'll just look at the W0 and W2 component. And it's labeled S in the diagram here, but it's the same thing. I'm interested in the solution around unit radius. That's where the bump is, and that is where vortex formation takes place. So that's what I see in numerical simulations. And in the so-called co-rotation region that's around unit radius, the solid line is much bigger than the dotted line. So the zero component is much bigger than the W2 component. What that means is the instability is predominantly two-dimensional. So if you're only interested in the growth rate of this instability, then you can get a pretty accurate answer by just doing a 2D calculation. And there are rigorous reasons as to why this instability is two-dimensional. But the quick check I did was to look at the expression for the vertical velocity perturbation. Is the ratio between the vertical derivative of this enthalpy perturbation and the intrinsic frequency. Now my region of interest is where the intrinsic frequency is basically zero. So the denominator is zero in the region I'm interested in, so I expect dWdz to also be small in order to keep delta Vz regular. So from this single expression here, I think this plot here makes sense, the fact that the dotted line is much smaller than the solid line. So here's a plot of the perturbation, the perturbed velocity field in the midplane, that's the arrows, and the colors are the enthalpy perturbation. So I've chosen to plot the solution around a positive enthalpy perturbation, that's an overpressure or overdensity. And the arrows here, the sense of rotation given by the arrows here is anticyclonic. That is to say, the rotation sense is opposite to the background rotation. So anticyclonic vortices are associated with overdensities, and that is a generic thing to find from linear instability calculations like this, and also full hydro simulations. Now, the whole point of doing a 3D calculation is to find out what is the vertical structure. Right? So in the next slide, I'm going to take a cut in the along this line, along the middle of this vortex, and I'm going to plot the RZ plane. And I'll look at what the velocity field looks like in that plane. So everywhere in this plane, at that particular azimuth, the flow is basically horizontal everywhere, except at co-rotation. At unit radius, the flow is actually upwards. And at this point, it's interesting to compare this to another simulation by Harries-Mayhew. So she did a couple of polytropic disk simulations of the Rossby wave instability, and she finds, of course, vortex formation, but also in the centers of these anticyclonic vortices, she finds upwards motion. So these are streamlines from one of her simulations for an anticyclonic vortex, and the flow is from blue to red. So the flow is upwards at the anticyclonic vortex. And what she found, also interestingly, was if she added dust to this vortex, then if the dust is small enough, then it can be lifted by this vertical flow to the disk surface. That means, so that could have very interesting observational consequences. Now, of course, it doesn't really make sense to compare this full hydro simulation to my linear solution, but it is still interesting to note the qualitative similarities, and does make physical sense because if you're trying to make an overdensity by shuffling material together, like concentrating the stuff towards unit radius, then the fluid will want to move vertically, right? Because it's got some stiffness. So that makes physical sense. Now with a linear problem, you can very easily vary the equation of state. So remember we have this parameter, the polytropic index, n. Now these are linear calculations done for different polytropic indices. The top one is say for n equals 1 polytrope, and the bottom one is n equals infinity. Now the n equals infinity case is basically very compressible, and n equals 1 case is not very compressible. So if I make the fluid more compressible, then the magnitude of this vertical motion diminishes. And that kind of makes sense because if I'm trying to increase the density by shuffling stuff together, indicated by these arrows, then if the fluid is very compressible, then the density along unit radius here, it can just increase, no problem. But if it's not very compressible, that is to say, if you lower the polytropic index, then as you try to shuffle material together towards unit radius, it's going to want to move upwards, or at least it's going to want to move vertically in order to conserve mass. It moves upwards because, of course, the midplane, I've adopted a even symmetry boundary condition, so it's reflecting. So shuffling material in pushes the stuff upwards. That makes sense. So the important thing from this plot is that vertical motion may depend or is a function of the equation of state. So the natural next step in the story is to include an energy equation property. So I now want to discuss adiabatic three-dimensional disks. So I'm going to continue working with a polytropic background disk. So in the equilibrium state, pressure will still be a power law function of density, but now I'm going to relabel my polytropic index as big gamma here. I'm now going to include an energy equation for the problem, and I'm going to say the entropy is conserved following a fluid element. So I go through the linearization procedure, and I obtain two partial differential equations. The V's are partial differential equation operators. W is my pressure perturbation. Q is my density perturbation. Now we are in a non-barotropic disk, so in general, W and Q are not the same. The previous set of calculations is a special case where the two gammas are equal. This is now a more general case where the two gammas are not equal in general, and therefore W and Q are in general not the same. And the difference between W and Q, we can define that to be the entropy perturbation. So the most natural definition for entropy perturbation for this problem. So anyway, but before looking for numerical solutions, it's important to have at least a rough idea of what the solution ought to look like. Because if we're doing this problem numerically, then having an idea what the solution looks like gives us a very quick way of checking whether the solution makes sense or not. So I want to sidetrack a little bit and talk about this quantity, S bar. I'll explain why I'm interested in S bar in a couple of slides, but right now we'll take it as a definition. It's defined to be the density perturbation minus some number, gamma over gamma, multiplied by the pressure perturbation. And I want to think about how this quantity should behave in the meridional plane. In the midplane, for example, I know the instability takes an axisymmetric ring and breaks it up into non-axisymmetric blobs. So here's a schematic diagram representing these non-axisymmetric blobs. And I'm going to pick one of these blobs and with overdensity and overpressure because I'm interested in vortex formation. And I'm going to ask, what is the distribution of S bar along this dashed line in the meridional plane, in the RZ plane. So if we go into that plane, I can argue various things. So this particular quantity S bar in this plane should have the following properties. I can argue that it should be negative at unit radius in the midplane. It should be 0 at the top, at the upper boundary, and therefore it's probably going to be a negative number going from unit radius in the midplane to the top, so along this dotted line here. I can also argue that it should be a decrease, its magnitude should decrease away from the unit radius because, well, I want to find radially localized perturbations. So, and I can make all of these annotations without doing any actual calculations. This is without solving any fluid equations. We can very quickly compare our sketch work, that's the top plot here, to a numerical solution to the linear eigenvalue problem. And as far as guesswork goes, the agreement is actually pretty good. And I'm interested in this quantity S bar because it turns out S bar provides, it's a barometric source term for vertical motion, Vz. And if this quantity S bar is not uniform in the meridional plane, that is in this particular plane as shown here, then the gradient of S bar is a source for vorticity, particularly as a mutual component of vorticity. That is to say, if S bar is not uniform in this plane, which is the case here, then you might get swirling motion, or also vortical or circular motion in this plane, which corresponds to generating azimuthal vorticity. So, that's something we can look out for. And quick note on the numerical method. In the previous case, we were doing this spectral approach, so we are we're writing the vertical dependence in terms of these Eigenbauer polynomials. I'm now going to take a slightly different approach, which is the pseudo-spectral method. So in the pseudo-spectral method, we're going to use finite difference in radius, but for the vertical dependence, we're going to expand the vertical dependence in terms of some set of orthogonal polynomials. Now, in these kind of problems, it's conventional to use Chebyshev polynomials. Anyway, the point is, we convert the original partial differential equation to a matrix equation. So we're not converting it to an ODE first. We're directly converting the PDE to a matrix problem. And then we just put the matrix into a matrix solver. Now this numerical method is much simpler to use, so it's much more practical than the previous method, and also gives us freedom to impose different vertical boundary conditions. But the downside I found was I had to guess the eigenvalue of the mode to good accuracy. And that's not a huge problem for me because I've done the polytropic disk problem, so I know what the eigenvalue should be. So this actually worked out pretty well. So we now go through another example problem. This is the basic state of my adiabatic three-dimensional disk. I've plotted here the epicyclic frequency plus the Brunt-Weissler frequency squared, and as a function radius for three heights: the midplane, solid line, and near the upper disk boundary, the dashed line. So this particular quantity, the Brunt-Weissler frequency, gives rise to this vertical dependence. So that's basic state, and we want to look for instabilities associated with this radial structure here. So this is the result of the linear eigenvalue calculation. I'm now plotting the eigenfunctions as a function of radius at three heights. So we're now plotting the solution in physical space. We'll just look at the enthalpy perturbation here, or actually this is the pressure perturbation. So it's very similar to the previous case. Most of what is going on is still localized to unit radius around this bump here. And interestingly, the magnitude of perturbation increases slightly away from the midplane. But it's very similar to the previous polytropic disk case, and the growth rate is again very similar to that case. It's only very slightly more unstable in the adiabatic case. This is a plot of the perturbed velocity field in the midplane on the left and near the upper disk line on the right. The color here is the entropy perturbation. So the entropy perturbation has some vertical dependence. It actually becomes more negative away from the midplane. But the velocity field is again very similar to the polytropic disk case. So we have anticyclonic motion associated with overpressure or overdensities. So that's not changed. But if we now go into, again, we'll take a cut in the middle of this vortex and plot the velocity field in the meridional plane. And this is what we find. This is very different to the polytropic disk case. We are now seeing vertical motion in the RZ plane in the case where the two gammas are not the same. So this goes back to my point about the fibroclinic source term providing azimuthal vorticity. So this is qualitatively different from the polytropic disk case. Now in the next slide, what I'm going to plot is the vertical velocity as a function of height at unit radius for a couple of different simulations. So this is the plot. We will just look at the solid line and the dotted line here. The solid line is the case where the two gammas are the same. So that goes back to the polytropic case. The dotted line is the case where the two gammas are a little bit different. So that's the more general adiabatic case. Now, in the solid line, the vertical velocity is a linear function of height. Okay, but changing the polytropic, or increasing the difference between the polytropic index and the adiabatic index gives me a different profile. And I think this is actually quite a noticeable difference between the dotted line and the solid line, given that the polytropic, the indices don't differ too much. I mean, they differ by less than 10%. So then you can ask, well, is there anything qualitatively different between the solid line, which is a disk with uniform entropy, and the dotted line, which is a disk with a slightly non-uniform entropy? So I looked up a review article by Cato, and this is a review article on oscillations in thin disks. So he was focusing on black hole accretion disks. But it turns out that if you're in a disk with a non-uniform entropy, then there's in general two different contributions to the vertical velocity. The first contribution, as this term here, represents pressure forces, because W is pressure perturbation, so this is due to pressure forces. The second term here, well, rho times dV dz, well, that's just vertical gravity. So the second term here is buoyancy. So in general, you have these two different contributions. But in the special case where there's no entropy variations, so uniform entropy, there is only one contribution to vertical velocity. So these two expressions for the vertical velocity is, I guess, qualitatively different. And also, if we go back to this more general case, we can compare the magnitude of pressure contribution to the magnitude of buoyancy contribution. And that is proportional to the angular frequency squared divided by the von Weissler frequency squared. Now, the angular frequency is not a function of height in this model, but the buoyancy frequency is. It increases with height. It actually diverges with height. So eventually, if you go far away from the midplane, buoyancy will always overcome pressure. So buoyancy eventually becomes dominant. So I think that is a qualitative difference between a uniform entropy disk and a non-uniform entropy disk. The origin of vertical motion is buoyancy in one case and pressure in the other. Okay, so as I mentioned earlier, my main application really for doing all of this is to check my hydrodynamic simulations. So here's a comparison between a Zeus full hydro simulation and the calculation from a linear problem. And the agreement is pretty well. So this is for the disturbance in the midplane. It also agrees quite well in the meridional plane. So this is the perturbation in the RZ plane. In both cases, I have this swirling or vortical motion in the meridional plane due to baroclinity, and the eigenvalues or growth rates and frequency of the mode agree well as well. So this is very encouraging. So this is the, it's only with this comparison I can be confident with a full hydro simulation like Zeus. But from these plots, you can see that disturbance actually extends pretty much vertically throughout the column of the fluid. So we can ask, well, are vertical boundary conditions important? I mean, if I do things to the top of the disk, is that going to affect the solution in the bulk of the disk? So this brings me to a more recent work. So we want to look at what is the effect of vertical boundary conditions. So I'm going to look at the special case of vortex formation through this Rossby wave instability in the case of a planet opening a gap. So here, these are Pluto simulations where I put in a giant planet. So I've got a Jupiter mass planet here. I've chosen the viscosity profile of this to be quite low, and it's well known that if you do this kind of simulation, then the planet would open up a gap, but the gap will be unstable to vortex formation. So this is a pretty standard result. You get a couple of small vortices, they merge, and at the end of the simulation, you get one large vortex orbiting the gap edge. So this is a case where the viscosity is about the same everywhere. So then I asked, well, what if I just put in a viscosity profile that looks like this? I'm going to maintain a low viscosity midplane, an alpha viscosity of about 10 to the minus 4. But I'm going to append on top of that a layer with high viscosity of alpha of 10 to the minus 2. And we'll do the same experiment, put a giant planet at unit radius, and see what happens. And in this case, I do not get vortex formation. You may see some sort of disturbance happening, but the result is very different, very distinct from the previous case. The gap edges is pretty stable. There's no distinct lump of fluid there. So the lesson here is that if you want to know whether vortex formation can take place through this Rossby wave instability, you may need to have a knowledge of the vertical structure of the disk, because this instability could be affected by vertical boundary conditions. Another effect, which I want to talk about briefly, is self-gravity. Now, these vortices are overdensities. They are overdense blobs. So you may think that, well, maybe does the weight of the vortex have any effect on the dynamics on the system? And also, self-gravity is also relevant because I talked about the fact that this instability is associated with the potential vorticity profile or vorticity profile of the disk. And vorticity profile of the disk, the vorticity is actually related to the Turner Q parameter, which is, of course, used to characterize self-gravity of the disk. Now, it turns out that in a linear problem, linear 2D problem, self-gravity, that is the disk gravity, actually stabilizes this vortex instability. And you can prove this formally, but a quick way of seeing that is to go from the linearized equations, you can derive an equation which has dimensions of energy. So what you can then do is look at this equation and say, well, for this vortex instability, this equation can be simplified a little bit, and you can try and balance different terms on either side of the equation. And the balance works out this way. The balance works out such that the left-hand side of this equation is positive for this vortex instability. But the right-hand side, whether it's positive or negative, depends on the strength of self-gravity. So I've got a positive left-hand side for this vortex instability. That means, of course, I need to have the right-hand side to be positive. Right? That means I need self-gravity to be sufficiently weak. If self-gravity is very strong, then the right-hand side will become negative. So it becomes impossible to have a balance. I've got a negative right-hand side and a positive left-hand side. So that doesn't work. So the only way this balance can make any sense is if the self-gravity of the disk is sufficiently weak. In 3 dimensions, there's an additional effect, which is vertical self-gravity. The vortex is an overdensity, so it has some weight. It's going to provide some sort of additional vertical acceleration. And this is a comparison between two simulations I did. These are three-dimensional Zeus simulations. I've taken a cut in the meridional plane across one of these vortices. And these simulations are the same, except in one case I've switched off self-gravity. In the other case I've kept it on. Now in the unperturbed disk, in the initial conditions, this disk has a Tudor parameter of about 8. So it's pretty much non-self-gravitating in the unperturbed disk. But once I get vortex formation, I'm generating overdensities. Vertical self-gravity does make a difference, even though initially it's non-self-gravitating. In the perturbed state, having self-gravity, having this extra vertical acceleration can make a difference. The point here is that the extra vertical gravity or extra weight of the vortex compresses the vortex itself. So you have a slightly more dense midpoint. So, well, my interest right now is even more massive disks. What happens if we go to even more massive disks? Now, it turns out that gap edges are no longer unstable to vortex formation, but they become unstable to this gravitational edge instability. This is a very particular type of gravitational instability that's associated with disk structure in a self-gravitating disk. So this kind of instability is well known in the galactic context, so particle disks, but it's only recently made its way into protoplanetary disks. And the relevance here is that, well, planets open gaps, and if the disk happens to be massive, then you can ask, well, is the gap stable? So in the bottom 3 plots here are a series of simulations I did over time of a giant planet interacting with a self-gravitating disk, done with 3 different hydrocodes: Zeus in 3 dimensions, Pluto in 3 dimensions with self-gravity, and the Fargo code in 2 dimensions. And these are not meant to be code comparisons. These are just things I did over time. So the setups are not exactly the same, but the qualitative result is the same. Now, this is very encouraging because we've got 3 different numerical codes, so that's different numerical algorithms, 2 different geometries, but very similar results. So this instability is real. It does exist. I want to point out that this instability is distinct from the Tudor instability. So we have an analytical description of this gravitational edge instability, and our model only makes sense if the edge is sharp enough. So what I'm saying there is, well, although this is a gravitational instability, you can get away with the Tudor parameter not being close to unity. I can have Q at the edge to be larger than 1, but I can make up for that by having a sharper edge and still get instability. But so my main interest right now is what is the effect of this gravitational edges on the orbital migration of the planet, right? Because I've got a big overdensity here. I'm expecting some kind of gravitational interaction between this big spiral arm and the planet. How does that affect orbital migration? So let's go back to basics and think about giant planets in protoplanetary disk. Now, if I insert a giant planet in the disk, there are 2 types of streamlines fluids can go on. If you're far away from the planet, then you just go on, then you just pass by the planet and you keep going around the central star, pretty much on the original Keplerian orbit. But if you are a fluid element that is within the so-called co-orbital or horseshoe region, then as you approach the planet, you would go on these horseshoe turns about the planet. So, for example, if you were this particle, you would approach the planet from upstream, and you would go from a larger orbital radius to a smaller orbital radius by going through these U-turns. And because you've changed orbital radius, you have lost angular momentum. That means the planet would have gained angular momentum. So particles or fluid which are on these horseshoe orbits exert a torque on the planet because they go through these turns. But in the normal case of just a planet, a giant planet in a stable disk, you don't really expect a lot of torques to come from these horseshoe orbits because we expect the planet to open up a gap. We expect it to clear this corporeal region of material. So we don't expect a lot of rotation torque in that case. But if the gap is actually unstable, so for example, in this gravitational edge instability example, the gap edges are unstable, then what the instability can do is, so here I've got this red blob here representing the spiral arm, the instability can reload these horseshoe orbits with material. That is to say, the instability can put material back onto these horseshoe orbits to interact with the planet. So, in effect, the instability can now provide a co-rotation torque on the planet. So here's the example. So I'm plotting here the torque contributions from different different radius away from the planet. So at the planet's orbital radius, I've got a large spike here. So I've got co-rotation torques due to this horseshoe effect, due to this instability supplying material to go on those orbits. So positive torque on the planet means outward migration. So here's a plot of a 2 Jupiter mass planet interacting with 3 different disk masses. The dashed line is the least massive, dotted line a bit more massive, and the solid line is most massive disk we've considered. And as I increase the disk mass, that is, I'm increasing the gravitational instability, this gravitational edge instability, I migrate the planet outward more rapidly. Now it's clear that this interaction, I mean, this is a very complicated system, and there are lots of parameters you can vary. One of the parameters is planet mass. The instability clearly will depend on the gap structure, and the gap structure depends on planet mass. Planet mass is, of course, a crucial parameter in orbital migration of the planet. Migration also depends on gap structure, right? So all of these things are connected. So we recently looked at the effective planet mass on this instability. So this is a project done with a summer student last year, Ryan Clute here, recently submitted. So the effect of planet mass on this instability and therefore migration is not obvious for the following reason. So here's a plot of the gap profile in terms of the tumor parameter Q. For two different planet masses, the solid line for a 1.5 Jupiter mass planet, and the dotted line is a 2 Jupiter mass planet. So as I go from the solid to dotted, I'm increasing the planet mass and making the gap edge sharper. This peak is larger. So that should promote instability, and therefore that should increase the torque magnitude coming from these spiral arms, which is due to the instability. On the other hand, if I'm increasing the planet mass, I'm expecting to deplete this orbital region, right? That is reflected by the fact that Q dotted line here is bigger than the solid line. So the density, the gap density, is actually larger in the solid line. Anyway, you increase the planet mass, you expect to deplete the orbital region of material, you expect to lower the surface density, and therefore you would expect to decrease the magnitude of torques coming from this co-orbital region. So it's not obvious at first which is more important. So Ryan Clute here did a couple of simulations varying the planet mass while keeping the disk model fixed. And what he found was it is the effect of the planet mass on the sharpness of the edge. That is really what matters. So here are 3 simulations. As I said, same disk model for different planet mass. Solid line is the case for 1.3 Jupiter mass, dotted line 1.5 Jupiter mass, and the dashed line 2 Jupiter mass. So as I increase the planet mass, I'm increasing the instability strength, and therefore making the planet migrate outward more rapidly. And this is despite the fact that increasing the planet mass should make a deeper gap, and it does make a deeper gap on average. So on average, the gap has lower surface density in the 2 Jupiter mass case, but it nevertheless migrates outward most rapidly. So anyway, the very interesting case with the 1.3 Jupiter mass planet, it looks as if the planet has reached some sort of equilibrium state where there is very little net migration. So we thought maybe we found a case where the planet, the positive torque being provided by these unstable spiral arms is balancing out the limit lap torques. The limit torques are associated with the wakes induced by the planet. So that's these two streams here. These things typically provide a negative torque on the planet. So the typical result for planet migration is inwards. But these spiral arms, due to this instability, is providing a positive torque. So in this particular case, the 1.3 Jupiter mass planet, we thought maybe we've reached some sort of balance between the positive torques provided by the unstable spiral arms and the typically negative torques provided by these wakes. But it turns out that picture is a bit naive. So Ryan simulated this system even further, and he found, well, only in addition, only 21 orbits, the planet interacted very strongly with the outer disk and is essentially scattered outward. And this picture of balancing torques is a bit naive because if you think about it, what we've got is a planet in a gap, and we've got large-scale spirals sweeping past the planet constantly, going by. And every time one of these spirals goes by the planet, it provides a positive torque. And sometimes, eventually, one of these spiral planet interactions is strong enough such that to promote the planet to migrate outwards into the outer disk. So that leads the planet into this configuration where there's a heavy overdensity ahead of the planet and underdensity behind the planet. So this is a classic configuration for Type 3 migration. And Type 3 migration is known to be self-sustaining, so once the instability or the spiral planet interaction gets it into this configuration, the planet runs away into the outer disk. Now, we're not very confident as to what happens after this jump, after 18 units here, because our computational boundary is actually pretty close to the maximum radius here. But we think this outwards jump is real because we see it for other planet masses as well, and also for other resolutions. So the application is planet formation by gravitational instability at large orbital radii. So we now have direct images of planets on large orbits. The classic example is HR 8799 and maybe Fomalhaut B. So one idea of forming these wide orbit planets is disk fragmentation. So you take a massive extended protoplanetary disk and you let the outer parts become gravitationally unstable, and they fragment into clumps, and there you have it, your big planets on large orbits. But in practice, there are several difficulties. Zhu and Vorobyov simulated this scenario. So they took a massive disk, let it fragment, and see what happens to the fragments. And in most of the simulations, the fragment or clumps just fall in towards the central star. So the survival rate is actually pretty low. Only about 10% of the simulations show a giant planet surviving on a large orbit. And they only survive on a large orbit by opening gaps. So you've got a situation of a gap opening perturber in a massive disk. So that's the scenario we've been looking at all this time. So what our simulation says is there may be an additional difficulty to do with gap stability. So you need to fragment a disk at large orbital radii. That requires the disk to be sufficiently massive, and you need to have the right thermodynamics. Even if you fragment a disk, you need to keep the fragments on large orbits. You need to open gaps. Even if you are successful in opening gaps, you have to think about gap stability. If the gap is not stable, then you may not be able to keep the planet on that orbital radius. So our result is our results suggest there may be additional difficulties for this particular model for planet formation on large orbits. So anyway, now these authors were not looking for gap instabilities, but it's actually quite interesting to note that Zhu, for example, what they found in one particular case is they found a clump opened a gap, but the gap edges became unstable, and there were further clump formation at the gap edge. So that might be due to this gravitational edge instability. And very interesting result from the Vorobyov simulation is that all the clumps in their simulation, which survive on large orbits, they actually migrate outwards. slowly. It will never identify why they migrate outward, but it's actually quite interesting to note that. Outward migration is what we see in our simulations. So right now, I'm still working with Ryan Cloutier, and we are basically right now redoing everything to do with gap formation in a self-gravitating disk by including the energy equation. So we have this additional parameter, this cooling time parameter, which we're looking at. So this is ongoing work, and the results at the moment look pretty interesting. I've also got interested in thinking about, well, does this gravitational edge instability happen in other contexts? So I've been talking about gravitational edge instabilities associated with planet gaps. Another situation where it might be relevant is dead zones. So dead zones are where, well, accretion doesn't happens very inefficiently. So in general, mass will build up in dead zones, and if this dead zone has some edge in it, then I can imagine maybe a dead zone boundary can be unstable to its gravitational edge instability. So these are preliminary simulations done with the Pluto three-dimensional code and the Fargo 2D code. And this is a disk with a viscosity jump at unit radius, and the disk mass is actually pretty high, although it is still gravitationally stable in the tuner sense. So it's actually quite interesting to see, well, first of all, the correspondence between 2D and 3D, and also the fact that, yeah, you can have this gravitational edge instability due to difference in viscosity. And it's very interesting to think about, whether or not, because these are intrinsically very global instability, right? The spiral arm extends throughout the entire disk. So it's interesting then to ask, do I get any kind of global transport, global angular transport? That's quite interesting. But this is actually very preliminary. And of course, at some point in the future, we would like to think about MHD. So want to think about magnetogravitational instability. In principle, we do have the tools already. For example, Pluto is a MHD code, and I have a self-gravity solver for it. So that opens up a very exciting possibility. So anyway, that is the end of this presentation. Thank you.